Good morning. It's my very great pleasure to introduce Swabha Swayamdeepta, who is a PhD student at CMU, currently at the University of Washington as a visiting student. She is also, you are currently an intern or was an intern?
I'm currently an intern.
An intern at the Allen Institute. She's working on structured prediction for natural language. She's done a lot of interesting work on how to incorporate syntactic cues, structural information into large data sets. And today she is going to be talking about learning challenges in natural language processing. Thank you.
Thanks, Chris, for the introduction. So I want to start off with some good news. So we seem to have made it in NLP based on headlines like this that we see in prominent newspapers. So this New York Times headline is actually talking about something called language models, which if you haven't heard of, takes some history of utterances and based on that predicts the next word. So based on the context, predicts the next word. And language models are not something new. They have been around for a long time, but the innovation here is contextualized representations. So these are representations that come out of language models. If you take whatever neural network you use for the language model, if you take the representations of words in that model, you get these contextualized representations, which are a replacement for the traditional word embeddings, because now you have the embedding for a word in context. And this is great because language models do not require any labels that you require in other supervised NLP tasks. All you need is a lot of text. And so these models can condition on part of the text to predict the next part of the text. And so we can use very large data sets. And so these models have been super popular recently and have been named very cutely Elmo and Bert, among others. And when you plug these contextualized representations into supervised tasks for which we do not have a ton of labels, we get a boost in performance. So just to pause here a little bit, this is really good news. We have learned how to use unlabeled data to improve the performance of supervised tasks, which have very little labeled data. So that's great. Now let's take a little bit of a closer look. So this is one of the supervised tasks I was talking about. It's called reading comprehension. So the task is you're given a passage, like this passage about colonists and migration here, and you're asked a question, the number of some colonists declined after what year? And so the task of the model is to select a part of the passage which answers this question. And in this case, it's 1700, which I've highlighted here. And Elmo gets it right, or Bert gets it right, sorry. And this is very impressive because if you read the sentence that actually contains the answer, it's a fairly complicated sentence. So it kind of tells you that, yeah, maybe Bert is doing some amount of reasoning. So that's great. Now, if we add another sentence to this passage, which looks kind of like the question itself, but does not answer the question at all, suddenly Bert gets the answer wrong. So this should be very disappointing to everyone here because the assumption that we made was that we were able to do some reasoning on the original sentence to get to the answer. But looks like it is only looking for these pattern similarities between what we'll call the distractor sentence, the one that we introduce later, and the question itself to make its prediction. So this is not great. So this leads us to the challenges I will try to address in this talk. The first challenge is it possible to incorporate some kind of prior knowledge about language so as to improve our NLP models? And for that, I'll talk about my work on syntactic scaffolds for semantic structures presented at HMNLP. And the second question is there something in the data that is helping these models get the predictions right, or even wrong for that matter? And we look at this in the second part of the talk in our paper on annotation artifacts in NLI data. All right, so let's dig a little deeper into that first challenge. Can we incorporate some priors about language? So if we look at this sentence, which contains the answer, you see that there is some migration event that it talks about, and then there is some decline event, and they're both connected by that year, 1700. And in order to answer the question properly, you have to look at different parts of the sentence and figure out the structural connections between those. So one way of thinking about the priors that can help us with these tasks is linguistic structure. So the question now becomes, can linguistic structure act as an informative prior for our models, our NLP models, deep learning? All right, so what does linguistic structure look like? So we start with the this notion of semantics, which tells us who did what to whom. Now, semantics is a very wide term. It's used in multiple contexts in NLP. So we are going to only look at some kind of shallow semantics, which tell us these who did what to whom kinds of questions. So to give a concrete example, let's consider a simpler sentence. After encouraging them, he told them goodbye and left for Macedonia. If we look carefully at this sentence, there are three kinds of things that are happening here. There's an encouraging, there is a telling, and there is a leaving. So each of these individual events is composed together to form the whole sentence. So if we look a little more carefully at one of these events, this telling event, this corresponds to a predicate. A predicate you can think of as a very basic unit of meaning, and information about predicates has been collected very painstakingly by linguists over the years. And if we look a little more closely at the predicate, there is someone who's doing the telling, there is something that is being told, and there is someone that the telling is being done to, or is the patient of the telling. So these are classified as argument 0, 1, and 2 of the telling predicate. And there is also this temporal argument, which is telling us when is the telling being done. So these arguments are predicate specific, so they have definitions based on what the predicate are, and arg0 typically corresponds to agent, and so on. So similarly, we have encourage as the predicate and arg1 or them as its argument, which gives you a different kind of predicate argument structure. And there is another one for leaving. It has its own arg0, arg2, and so on. So that's great. So this gives us some very shallow way of organizing all the things that are happening in the sentence, and we do this in multiple layers. So this kind of semantics is called broad coverage semantics, and this is a span-based formalism because the arguments are typically realized as spans in the text, and by span I mean a contiguous selection of words in the sentence. Now, this is also an example of structured prediction because the label at any position is dependent on labels of the other positions. All right, so one thing that is troubling in this kind of predicting these kinds of structures is that we do not have a ton of data. We have like tens of thousands of examples, but that is not enough because if you see carefully, this is a lot of information, a lot of labels that we are trying to predict in a given sentence. And so we need lots more data to do this. Any questions so far? All right. So is it possible to look at a little more level of granularity to figure out how we can get to these semantic structures more easily? So syntax gives us one of these solutions. So syntax gives us a foundation on which we can represent the meaning of the sentence. So one example is for the same sentence, the syntactic tree looks something like this. So all that is happening here is that there is a top-level node which generates the full sentence, and we have phrases that gives us the preposition, which is the PP, the verb phrases, VP, and noun phrases, NP. And these are all hierarchically organized as a tree. So if we look carefully at any of the nodes, this also corresponds to a span in the sentence. For example, this prepositional phrase corresponds to after encouraging them if you go down all its descendants up to the leaves. So because this corresponds to different spans in the sentence, each node corresponds to different spans in the sentence, maybe there is some similarity with the kind of span-based semantics we just saw before. And that is exactly right. The arguments and predicates that we saw in the last slide correspond exactly to these semantic or syntactic nodes. So that's great. But as you can see, these tree structures are also fairly complicated. So we have arguments that overlap with some of the nodes, but there is a lot more that's happening in the tree that do not really matter as much for the semantics. So the key intuition we are going to use here is that it's good that we have these multiple kinds of structure. We can use them as complementary sources of supervision, but at the same time, we don't need to go into the complexities of one in order to predict the other. So this is the basis of the work that we did at EMNL P28, and this is with my co-authors Sam and Kenton and Luke, and my advisors Chris Dyer and Noah Smith. Any questions so far before we go? Okay, cool. So here, the setting we are concerned with here is structured prediction with some sort of intermediate structures. And as we saw, our intermediate structures are going to be syntactic. So typically, other syntactic structures are POS tag sequences or different forms of syntax. And here we are going to look at phrase syntactic structures. So in this setting, we usually follow a pipeline. Given the input, we first predict the intermediate structure, and given that intermediate structure, we predict the output structure. Now, on the one hand, it is great because we can use different sources of structural supervision. So we have essentially more data to make this prediction. But at the same time, we have this problem of cascading errors. So if we make an error in predicting this intermediate structure from the input, those errors cascade to prediction of the output structure. And that's not good. So as an alternative, people have come up with end-to-end models, which go directly from the input to the output structure. But this also comes at a cost, as people have recently started finding out. We have something still to lose if we do not take into account syntactic information. Okay, so this raises two questions that we tried to answer in this paper. Is it possible to leverage intermediate syntactic structure without making the full intermediate structured prediction? So without predicting that full tree, can we still be able to use syntax? And the second question is, even if we were to predict the syntactic tree or parts of it, can we do all of it at train time and not have to deal with it at test time? And the short answer is yes. We saw this for 3 different tasks. In the interest of time, I won't go through these tasks in detail, but they are some variation of span-based semantic structure prediction. All right, so to give a little more context about where our work falls in the larger scheme of things, let's consider this graph with 2 axes. So on the y-axis, we have the amount of syntax we need for training, and on the x-axis, we have the difficulty of designing and training these systems. So we saw that end-to-end modeling does not require any syntax, and we saw that syntactic modeling, syntactic pipelines are kind of clunky to train and can get into this cascading error scenario. Another way of incorporating syntax is to use latent variables for syntax. Now, this is great because you're not like relying on any external system, but at the same time, these are very hard to train because you need to marginalize over very expensive syntactic trees, and that runs into its own problems. Another variation is joint modeling. So here, from the point of view of the model, we have a single task, and the single task may have syntactic components and semantic components, but the model is agnostic to that. And this is also great, but it runs into its own complexities. If you're curious, we have some work that I can talk about offline. Now, a simplification of this joint modeling is multitask learning, where we were inspired by, as a community, we were inspired by work by Haldome, where we have task-specific, or in his case, domain-specific parameters in the frustratingly easy domain adaptation setting. And each task has its own parameters, but there are parameters which are shared between the tasks. So from the point of view of the model, you're doing two different tasks, but you're doing the tasks completely. So it's like full structured prediction of one kind, full structured prediction of another kind, and so on. We also have some more work in this setting, which I'm happy to talk about later. Now, the syntactic scaffolds work falls in this very nice little corner where we are going to use syntax for training, but we are going to remove all the difficulty of predicting that whole syntactic parse tree. So, so we get the benefit of both worlds. All right, so to be a little more concrete, we're still in this multitask setting, only that our intermediate or scaffold structure is no longer a full valid structure, but it is very, very shallow syntactic structures which are only going to be necessary in predicting our output structure. So what this gives us is this soft notion of syntax. So we learn syntax-aware representations, and at the same time, we avoid falling into or making those errors in the intermediate structured prediction phase, which go on to making the final output structure, mistakes in the final output structure. And since this is a representation learning approach, we can do all the work during train time and not have to deal with it at test time at all. All right, so again, to give an overview of the task, as our input, we'll use sentences or documents. As our output structure, we'll have these span-based semantic structures. And as our scaffold, we'll use phrase-based syntax, which you can see in this tree. All right, so how do we go about building a syntactic scaffold? So the first step is to figure out what the desired parts of the syntactic tree are for our output task. So here I have highlighted parts of the tree which correspond exactly to semantic arguments. And so the idea is that if we are able to predict what spans in the sentence correspond to these shallow syntactic labels, we should also be able to predict what spans, the same spans as semantic arguments. And in order to do this, we'll do a simple span level classification task. Here, X is our sentence, Z is a collection of all syntactic spans, and for every span, we make an independent classification by predicting what the label of the span is. All right, so that's the scaffold objective, and to train with these syntactic scaffolds, all we do is plug in the scaffold objective with a primary task objective by interpolating with a hyperparameter which gives us the mixing ratio between the two objectives. So here, X is our input, Y is the desired output structure. For our case, these are the semantic structures, and Z is the scaffold syntactic structure. So one thing to note here is that the primary data set on which we train the primary objective does not have to be the same as the scaffold data set. All we need to care about are these theta parameters, which are shared in both the settings, and these correspond to the input representations. And task specific, you have phi for the primary task and psi for the scaffold task. And to train, we can alternate between training a batch of the primary scaffold and the auxiliary or the scaffold task. And another way of training could be pre-training completely on the scaffold task and using representations to run the primary task. And so on. Any questions?
Is there any difference between the two different schedules?
So we saw that this particular schedule works better for us than the pre-training. That's probably because we don't have a ton of data to pre-train with. Off the top of my head, I cannot tell you what schedule works best. It's something we found empirically. All right, so now moving on to the primary objective. So in this case, the only consideration we had was that we should score the same kinds of structures in both the primary and scaffold task in order to make the most out of this parameter sharing approach. So remember, in the scaffold task, we were scoring each span independently, and in the primary task, we will try to do exactly that. So alternatives for the primary objective are either we can use a span-based classification just as we did in the scaffold. Maybe we can have some aggressive pruning to rule out certain spans. Another option is a semi-Markov conditional random field. So what does a semi-Markov CRF look like? So it gives us this model it gives us this globally normalized model to predict segmentations for a sentence. So a segmentation looks exactly like the predicate argument structure we just saw. So given a sentence, we are going to divide it into different segments where each segment either stands for a predicate or its argument. There is also this segment which does not correspond to anything, and we will mark that as a null argument. Now, because this is a globally normalized model, it gives us a probability distribution over individual segmentations. Now, it's a generalization of CRFs. In CRFs, we model the label at every position, and here, instead of just modeling the label, we also model the length of an input segment. So we decide that a segment has to be certain positions long and what the label of the segment should be. So each segment is a tuple containing the indices of the start of the segment, the end of the segment, I and j here, and the label corresponding to that segment. And finally, the score of an entire segmentation is the sum of the scores of each of these segments. Training and inference on this model is given by dynamic programs. These are of complexity O of n dl. N is the length of the sentence. If we are going to consider every possible span in the sentence, we would run into quadratic time complexity, so it'd be O of n squared. But we limit that by considering spans only of a certain length, which is d. So that is the d in the complexity, and L is the number of different labels. So that corresponds to this y.
Do these spans overlap? Because we've got, now after encouraging them, we told them goodbye as one.
Yeah, so
span, we've got the second one with the coordination there.
Yeah, yeah, exactly. So for a given predicate, these spans do not overlap, and that is the basic condition. And this is true for the kind of semantic structures we look at. That's one of the constraints for these structures. The segments should not overlap. There are some other constraints that you should not repeat some core arguments, which we do not follow. We don't have that constraint, so we can get this model can give us multiple labels for different segments, and the same label for multiple segments in the sequence. More questions? All right. So let's look at what the model looks like. So we start with the sentence in our running example. We start with some kind of word embeddings for each word in the sentence. These are passed through your favorite neural net encoder. We used a bidirectional LSTM. So the hidden representations of this LSTM then go into forming the span embedding. So we just take the hidden representations of the first word in the span and the second word in the and the last word in the span and concatenate to get the span embedding. We also add a span level attention. So this is an attention mechanism that looks at each word in the span, computes weights for it, and concatenates that to the span embedding. So once we have the span embedding, we can compute a scaffold score. So we can score the span based on the parameters of the scaffold model to get the scaffold score. And we can also compute the semantic score. These scores go into our objective that we just saw in the last slide. And one thing to note here is that we only learn the scaffold score when we have annotations of the syntax. And similarly, we only learn the semantic score when we have annotations for the syntax. So we need not learn both the scores at the same time. Depending on what data we are training on, we get these different scores. All that is common between the primary and the scaffold datasets are these span embeddings. All right, so moving on to some results. So we see that the scaffold task brings about an improvement over the primary objective. So this green line denotes the primary semi-CRF objective where we haven't plugged in any scaffold objective. And we get a huge gain in frame SRL and similar gains in the two other tasks we considered. So that's great. So to just recap, the question we started with was, can linguistic structure act as an informative prior for deep learning? What we wanted to get are these predicate argument structures for a sentence. We used syntax as our prior, and our approach wanted to make use of the syntax without getting into the difficulty of predicting an entire syntactic tree. And we figured this works, and this is shown in the empirical improvements we got in the 3 different tasks we considered. All right, so what next? We saw here that given a sentence, we were able to predict the semantic structure. And to do that, we used syntax as a prior or as an intermediate. So what can we do next? So you can imagine in the same way using semantics as an intermediate for downstream applications. Like remember the original machine comprehension example we had where we had a complex sentence. So we can think of the different predicate argument structures for that sentence and try to see if these semantic representations can help in tasks like the reading comprehension task. Another application is representation learning. So instead of just, sort of pre-training with the syntax, now we can pre-train with both syntax and semantics. Maybe we can use predicted semantics to get like large corpora, and hopefully the representations we learn from some sort of structural prior will give us even better performance in downstream tasks. All right, so another application which I'm very interested in is control generation. So we started with the sentence, and we were able to predict both syntax and the semantics. Now, suppose we were to alter the syntax a little bit so as to reproduce the sentence with some alterations. This is called syntactic paraphrasing and has been done before, but it has not taken into account the semantics of the sentence. So we can use the semantic structure as some sort of a constraint to ensure that the original sentence and the altered sentence mean the same thing. Even more interestingly, we can alter the semantics in some very, very controlled way to transfer certain stylistic attributes in the original sentence and the altered sentence, or we could transfer some attributes such as polarity, sentiment, and so on. And an application of this is, personalization. So we want certain things to be said in a different way depending on who's doing the talking. So this can be a very good application of this kind of predicted semantics. All right, so here I'll switch gears a little bit and I'll take questions.
Do you have any sense of how much the size of the primary task data affects the quality of the output? In other words, do you lose, for example, is the impact of the semantic and syntactic structures diluted by larger data sets, or if you use a larger data set, do you need as much annotated, supervised data?
Yeah, so that's a very good question. So if we use larger data sets, it always improves. But there's also this question of how much overlap we have between the data. So remember in I showed the setting where the primary data set does not overlap with the second data set. And in that setting, where the inputs are all the same and we have annotations for both syntax and semantics on the same input, even in that case, we see an improvement if we use the syntactic scaffold. So the improvement is not just coming from more data, like more input data, it also comes from more labeled data. And as to how much data is required to improve, we saw the more the merrier. So the more data we have with good syntactic annotations, remember we used gold syntax, so the more data is obviously going to be better. We didn't see that more data was hurting us at any point of time, but there is a limit to the amount of data we can use because there's only so much data. Okay. If there are no more questions, I'll move on to the second part of the talk. So remember how Bert was getting confused when it saw the new distractor sentence, which looked very much like the question? So one thing here is that maybe what is happening is there is something in the data, or there's something about the sentence which is making Bert change its original answer. So this makes us think about what in the data is actually responsible for our model's predictions. These predictions may be correct or wrong, but I think we should be looking a little more carefully at our data sets now. So this brings us to the second challenge, which we will look into the annotation artifacts in natural language inference data paper. This was presented at NACL and is work with my colleagues at UW and Sam Bowman from NYU. All right, so to start with, what is natural language inference? So you're given a premise, which is some state of the world that you're in. And then you are provided a hypothesis. And the task is to figure out whether that hypothesis is true, false, or neither given the premise. So an example of a premise is two dogs are running through a field. And the hypothesis is that the pets are sitting on a couch. And you have to predict whether or not this hypothesis is true. Any guesses? Everyone wants to be safe. Yeah, this is false, right? Like, it's a very simple task for us. Two dogs are running through the field. It's not the same as the pets are sitting on a couch. But from the point of view of a model, it has to figure out that two dogs is the same as the pets, and running is not the same as sitting, and field is not the same as couch, and so on. So there are some reasoning. There is some reasoning involved here. So the way these data sets are constructed is that annotators are shown a premise. So these premises come from captions in the Flickr data set. And they are asked to generate 3 different hypotheses, one that entails the premise, one that is neutral to the premise, and one that contradicts the premise. So using this kind of process, there were 2 big data sets that were built, the Stanford NLI data set and later the multi-NLI data set. The multi-NLI data set is in different domains. So one thing to note here is that the annotators did not have access to the image. They only saw the caption in generating these 3 hypotheses. Okay, so usually this is solved as a text classification problem. So you typically get some encoding for the premise, some from the hypothesis, and run this through your favorite model. Typically, you do some amount of elaborate attention mechanisms between the premise and the hypothesis and predict the final class as a classification task. So lots of progress has been made in this field. So since it came out, lots of systems have submitted the results to it, and our performance is now in the high 80s or even the low 90s. So that's great. And we started looking into this task, thinking it will be like a good test bed for this kind of semantic structure. We could use the semantic structure to figure out relations between the hypothesis and the premise. And we were running some baselines, and a very simple baseline we tried was we removed the premise and just used the hypothesis into a text classifier and use that to predict the class labels. So as an example of what that would look like, you're given this hypothesis. The little boy is diving off the diving board because he is an excellent swimmer, and you have to predict whether it's true, false, or neither. Any guesses? Wow, you're all smart. You're not, yeah, any guess would be wrong because this does not make any sense. There's no premise, so what does it mean that the hypothesis is true, false, or neither? So, but the model surprisingly gets this task absolutely right. Our simple model that does not take into account the premise gets this right, and 30 points or so above the majority class baseline for the SNLI data, and like 20 points or so above the majority class baseline over the multi-NLI data. So this really surprised us, and for a long time we thought we're obviously doing something wrong. And so we started looking at the data. And we saw that in different classes, when we considered entailment versus neutral versus contradiction, we saw different patterns in the data that we thought might be responsible. So for example, for entailment, the hypothesis seemed like a generalization of the premise. So some men and boys becomes people. Grassy area becomes outdoors. There's a lot of outdoors in the hypothesis. For the entailment class, there is also shortening. So you kick out some of the information in the premise and you just paraphrase the premise. Neutral artifacts contain things like modifiers. So you add attributes to certain entities in the sentence, which there is no way of figuring out whether or not is true, because remember, you don't have access to the image or anything. You just have access to the premise. Other artifacts were purpose clauses, where you attribute something is happening because of something else, which, again, there is no way to verify given the premise. Contradiction artifacts typically contain a lot of negation words like nobody, not, nothing. And my favorite one is dogs in the premise become cats in the hypothesis. So basically, if you see cats in the hypothesis, it's a very good indicator of contradiction. So, so this kind of tells us that there are these annotation artifacts. So these are kind of heuristics that the annotators followed to make their task simple. They wanted to generate as many as they could, all these hypotheses. And so they had this idea, oh, if we do these simple tricks, we probably will be able to be very efficient. But what that resulted in are these clues in the hypothesis which made the task of the model very easy. And we were thinking, like, how is it possible that all these annotators came up with similar kinds of tricks? And we saw one of the seed examples which were provided to the annotators, and they contained these artifacts, like they did the generalization in the seed example and so on, and the annotators just ran with it. That's the example they were trained on, and they did not do anything much more creative. All right, so the next question is it possible, now that we know that there are these artifacts in the data sets, is it possible to filter out these examples with the artifacts? So to do that, we did the simple thing where we used our unreasonable hypothesis-only classifier, and the examples that it got right, we classified as easy, and the examples it did not were hard. Now, we ran the state-of-the-art models, or we tested the state-of-the-art models on these hard and easy examples. And we saw that, yeah, not surprisingly, all of the performance, or most of the gain of the performance, is coming from solving the easy examples, whereas a lot of these systems are getting the hard examples wrong. All right, so we revisited this question. So have we now figured out how to make this data set usable by just filtering out these artifacts, these easy artifacts? And the answer is kind of disappointing, because hard examples, if you look carefully, have their own artifacts. So, for example, the neutral sentences, which were hard, contained a lot of these negation words. So that's its own artifact of its kind, and at that point, we started questioning what even is an artifact. And also the easy examples had these artifacts, but they were also valid examples. Like, sure, cats are not dogs. That's perfectly true. And so the model should not be devoid of learning from these examples, but at the same time, it should not have a ton of these examples that kind of like bloat the performance of the models. All right, so if you're thinking, oh, this data set is a weird data set, and sure, I'm not going to use it or whatever, there's no escape, because there are lots of these large-scale data sets which have the same problem, and concurrently to our work, people have come up with systems that look at these problems. So now that we are in a world where we have these large data sets and each of these data sets contain their own artifacts, what can we do about it? So can we still use these data sets? And the key intuition here is that the same models that can exploit the artifacts are the models which can detect the artifacts also. And to detect the artifacts, we can use some stylistic global features, like, for example, the length of the sentence and so on, to figure out what the entailment class is. And so the idea is to subsample these large data sets by weighting each example differently based on where on that hard, easy spectrum this data could fall. And this has a lot to gain from the kind of importance sampling or importance weighting work that has been done at MSR. So that's a future direction of interest. There's also this direction of improving the data collection process itself. So maybe annotators can be explicitly instructed to avoid following these simple heuristics, or we can collect annotations in batches. If we collect a few samples of annotation and see if there are problems in it, maybe we can update our instructions to make the annotators avoid those problems. But neither of these solutions is like very satisfactory, because they involve like manual inspection of the samples, and what is an artifact to me might not be an artifact to you, and so on. So another direction is to completely forego human annotators at all, altogether, and instead be able to generate hypotheses from premises by making small alterations. And this kind of ties into the application part from the last part of the talk, where we can take the semantic structure of a sentence and alter it in specific ways to generate a different kind of sentence, which is different from the original sentence in very specific ways. All right, so to recap, the two challenges we saw were that linguistic structure could act as a good prior for our NLP models. And we saw that there are things in the data that is causing our models to achieve this bloated high performance. So what's next? We should come down a little bit, and but not really. Like, we deserve a pat on our backs for getting where we are, but there are still a lot of interesting and open challenges. For example, we have just started scratching the surface of what we can do with predicted structure, and there is a lot more that can be done in this area. There's also a lot of work that can be done with the imperfect data sets that we have now by making sure we can utilize some of the parts of the data set which are still very useful. All right, thank you.
Questions? We have a few minutes.
So this is, I'm just thinking out loud here, so bear with me, but I mean, one could imagine with the multitask learning, to throw in sort of more and more natural language tasks, so we have the luxury of having labeled data.
Sure.
And sort of, you know, in the end, with the goal of learning sort of a universal representation that is sort of informed by multiple linguistic tasks, that then might be, you know, well generalizable outside of these tasks.
Yeah, for sure. And that's kind of what a lot of these new models for fine-tuning are doing. So they are getting trained on these large amounts of data and are just fine-tuning to the particular application. And I think it's a promising direction in general. Like, all you're doing is you are adding a lot of prior knowledge to the representations. But at the same time, I think there is a necessity to have something task-specific. You cannot just have like one. It's hard for me to imagine one model that solves every task, but you can definitely have a very strong prior.
Yeah, and that's actually what I meant. So not one model that solves all the tasks, but one model that generates a representation which can then be fed into like a task-specific
Yes, for sure.
learner as sort of an input.
For sure. One thing that we have seen, though, is that sometimes this kind of doesn't work as well. For example, and this might be just a function of the task we were looking at. So we took multiple languages. We took like these semantic representations in multiple languages. We joined them together, and we tried to train like one large semantic labeling model, and that model did not work as well. Like, we thought, we have all this data, the labels are fairly the same, and it should just work by using some kind of multilingual word embeddings, and it did not. So there are certain settings in which this works. So we got improvements in low data settings. And so I have never seen this kind of multitask learning not work in a low data setting. When there is a lot of data, then it depends on the task. Like, it works in some cases, like you were asking, but in some other cases, it may or may not work. So I guess there's no way to have the New York people. There's no way to have the New York.
Yeah, apparently not.
Yeah, okay. Yeah, that's all right.
The one question question or thought that I had with respect to that final data set case where there were people were given the image caption essentially and asked to provide It occurs to me that it might be possible to get a better set by finding similar images with captions.
Yeah.
And getting people to annotate those.
Yeah.
Because you would then be able to do multiple variations of
Right,
the
yeah.
You wouldn't get dogs and cats anymore quite so much.
Exactly. And like, so I think what you're trying to say is collecting these cases of entailment where both the premise and hypothesis come from their own distributions, but happen to be entailing each other or contradicting each other and so on. Yeah, I think that's a way to go, but it is also a very hard problem, right? Like, how do we find images which are contradictions of each other?
Right. Well, I was thinking images that appeared similar, for example, that were algorithmically somewhat matched.
Right.
Might have, two dogs chasing a ball, three dogs fighting over a stick. Might be very similar as images, and image detection algorithms might cluster those naturally. And you would get text that might either contradict or support.
Yeah, that is like a good idea, and I'm not sure if people have tried that, but people have definitely tried collecting just sentences independently and figuring out if they entail, and that honestly doesn't work as well. Yeah.
Okay. Well, thank you. We need to get you to your next meeting.
Okay.
Thank you very much.
Thank you.